Okay, let's do question 8. Question 8, part A. Before we start the notation, okay, sorry, brought the pen. Okay, I'll clarify the notation. I will use 1 as true and 0 as false in this case. Okay, so the first problem, they asked about the probability that A1 is true given that C is true. So the probability that A1 equal to 1 given C equal to 1. Use Bayes' rule to expand this expression. Probability of C equal to 1 over the probability that C equal to 1 given A1 equal to 1 times probability that A1 equal to 1. So the probability that A1 equal to 1 is equal to a half, because A1 is a Bernoulli random variable with parameter half, so it takes some value 1 with probability a half. Probability that C equal to 1 is equal to 1 minus the probability that C equal to 0. So 1 minus the probability that C is false is just the probability that C is true. So probability that C equal to false. So C is false only when all these M clauses are false, because they are all relationship, right? So look at each of the clause. For each clause, there are 4 ways to assign them. Either true, 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 false, false, true, or false, false. So out of them, 3 of the assignments evaluates the clause to false. So it's 3/4 of the probability that one clause will be false. Same here. So probability that C will be false is the probability that all M clauses will be false. So 1 minus 3/4 to the power of N. That's the probability that all M clauses would be evaluated to false. So C1 equal to, the probability that C equal to 1 is equal to 1 minus 3/4 to the power of N. Next, we look at the probability that C equal to 1 given A1 equal to 1. We break this into 2 parts. First part is C equal to 1 and B1 equal to 1 given A1 equal to 1. Second part is C equal to 1 and B1 equal to 0 given A1 equal to 1. Okay, so for the first part, given that A1 is true, the probability that B1 is true is just a half. So now that we know A1 and B1 are both true, so it means the first clause evaluates to true, which means that C will definitely be true no matter what's assigned to the rest of the N-1 clauses. So we times this by 1, because there's 1 probability C will be true. Okay, for the second case, given that A1 is true, the probability that B1 is false is a half. Given that A1 is true, B1 is false, then the first clause would be false. So we now pay attention to the rest of the N-1 clause. So for C to be true, the rest of the N-1 clause couldn't all be false. So we need to time this with the probability that C equal to true, given that B1 is 0, A1 equal to 1. So this further becomes 1 minus the probability that C equal to 0 given B1 is false and A1 is true. This probability is equal to what? We look at the rest of the N-1 clauses, and with 1 minus 3/4 to the power of N-1 probability that C, actually, my bad, it shouldn't be this. C would equal to 0 when would be false when the rest of the N-1 clauses are all false. So that happens with the probability 3/4 to the power of N-1. So bring this all together, it becomes 1 minus, this is not division, it's just a line, underscore. Okay, this becomes 1 minus 3/4 to the power of N-1. So this equation eventually becomes a half plus a half times 1 minus 3/4 to to the power of n minus 1. Now I'll plug these three all in the first equation. We get probability that A1 equal to 1 given C equal to 1 is, okay, the numerator is this part, which is here, a half plus a half times 1 minus 3 over 4 to the power of n minus 1 times this whole thing times probability of A, which is a half, and the denominator is C equal to 1, the probability of C equal to 1, which is here, 1 minus 3 over 4 to the power of n. So this is the answer for the first part. There's still another two different solutions, and I will present them now. Okay, let me erase this part. Okay, erase all of them, and okay, so the second way of doing this is to notice that probability of A1 equal to true given C is true is equal to the probability is equal to 1 minus the probability that A1 is false given C is 1 is true. So 1 minus this thing. We further break it down by base rule. C equal to 1, probability that C equal to 1 given A1 equal to 0 times probability that A1 equal to 0. So this we already know from previous parts that probability of C equal to 1 is 1 minus 3 over 4 to the power of n, and the probability of A1 equal to 0 is a half. So we need to do this part now. Probability of C equal to 1 given A1 equal to 0. So how do we know this? Okay, so we know that A1 is false, so which means that no matter what B1 is, the first class, this one, will be evaluated false. So for C to be true, we actually want to make sure that not all of the rest of the n-1 classes are false. So it becomes 1 minus the probability that C equal to false given A1 equal to 0. So what's the probability of C is false given that first class is false? Okay, so it means that the rest of the n-1 classes are all false too. So it's equal to 1 minus 3 over 4 to the power of n-1. This is the probability that all the rest of the n-1 classes are false. So this gives us this probability. Great. Now we plug in these to the original equation, which give us A1 equal to 1 given C equal to 1 is equal to, here, 1 minus this probability is just this we just get, 1 minus 3 over 4 to the power of n-1. This whole thing times a half. A half is here, right here, yeah, over probability of C equal to 1, which is 1 minus 3 over 4 to the power of n, as we got from part 1. This is also the solution. This is actually equivalent to the solution in part 1. There's yet another solution, another way of doing this problem, I should say. And let me erase this first. The last way of doing this is through counting. Since we need to, here, all these variables are IID Bernoulli random variables with parameter half, so this means each unique assignment of all the A and B has the probability, has the equal probability of occurring in the sample space. So we can use the counting way to do this. Probability that A1 equal to 1 given C equal to 1. It's the same as counting, right? So we just need to make sure, okay, we need to make sure the size is correct. So the size of C equal to 1, and the numerator is A1 equal to 1 intersect C equal to 1. We further break this part into two parts, depend on different B, A equal to 1 and B1 equal to 1 and C equal to 1, plus A1 equal to 1 and B1 equal to 0 and C equal to 1. Denominator is still C equal to 1. Okay? So these two are disjoint because B1 equal to 1 and B1 equal to 0 are disjoint. Now, how many ways are there to assign C? Like to assign the two indifferent random variables? Well, there are 2 to the power of 2n ways, which is equal to 4 to the power of n, because there are 4 ways to assign each clause, and there are n clauses there in total. So out of them, how many will be evaluated to false? 3 to the power of n of them, because for each clause there's 3 ways to be false. So 3 to the power of n ways exists for the whole assignment to be false, for every clause to be false at the same time. So here, now we look at the probability, the size of A equal to 1, B1 equal to 1, and C equal to 1. Given that A1 and B1 are both equal to 1, then we know the first clause is true. So the C will be true regardless of what assignment is given to A2 up until Bn. So the 4 to the power of n minus 1 assignments all satisfy, are all included in this event space. Plus, here, we know that A1 equal to 1, B1 equal to 0. So the first clause actually evaluates to false. So we look at the rest of n minus 1 clause. We know that there are 4 to the power of n minus 1 ways to assign them. But however, out of them, 3 to the power of n minus 1 would result in all false clauses, which means C would be false. So we subtract those parts from the 4 to the power of n minus 1. Eventually we get this answer, and this is also equivalent to the previous two parts, two solutions answers. Yes.